Okay, so let's look at damped harmonic motion. And so we're going to add a friction term. So we have, let's think of the spring first, then we'll think of the pendulum, and then the LC circuit. So we'll do the same thing for all three systems. For the spring that's stretched in the x direction, we have MA equals minus kx, but we're going to add a term that depends on the velocity or on the speed. So minus some coefficient, the mass, dx by dt. So it looks like that. And so our equation reads second derivative of x and t plus k over mx plus b dx by dt is equal to 0. And we'll motivate this for the LC circuit, but we could do the same thing here by, and for the pendulum, by considering that the fact that if we get rid of this term here, we know that the solution is a cosine function, cosine or sine function, and we can write that as an exponential with complex numbers. And so this will be easier to do when we get to the RLC circuit, but the general solution, including the cosine or sine function, can be written as a e to the alpha times t, where alpha is to be determined. It could be a complex number, it could, and that would be a cosine or sine function, or it could be a real number, in which case it would be exponential. It could be exponential growth or exponential decay. And so that captures all possible solutions. Let's look at two derivatives of this. Well, let's do first one derivative, where we have alpha a e to the alpha t. Two derivatives, we get alpha squared a e to the alpha t. And so we'll get a condition on alpha if we plug these into here, right? So x double dot, x dot, and x into there. We'll get an equation that looks like alpha squared plus k over m plus alpha b times a e to the alpha t, and that's equal to 0. And so we can divide that out. We get this equals 0, alpha squared plus b alpha plus k over m is equal to 0. That's just a quadratic equation whose solutions are minus b plus or minus square root of b squared minus 4k over m divided by 2. And so we have two possibilities, minus b over 2 plus square root of b squared over 4 minus k over m minus b over 2 minus the square root of b squared over 4 minus k over m. And so if we remember, we see usually omega equals, omega squared equals this k over m for the spring. And so we can say that the alpha is minus b over 2 plus b squared over 4 minus this angular frequency for the spring, or minus b over 2 minus b squared over 4 minus, sorry, this is omega squared. Looks like that. And so now we have different behavior depending on, so if the first term in the square root is greater than the angular frequency omega, then both solutions, so alpha, both solutions are alpha real and negative. And so the solution is really a sum of decreasing exponentials. So x looks like some a e to the alpha plus 1 plus b e to the negative 1 times t. And so displacements for the spring, in this case, just die with no oscillation. So displacements die down without oscillation. And if instead, if b over 2 is less than the omega, then we have an x equals some coefficient e to the minus b over 2 times t, and then we have a term with a square root of a negative, which looks like cosine of omega, well, a different omega plus phi kind of solution, where the omega prime involves that quantity there, because it appears under the with a minus sign under the square root. So that kind of a solution, and so this kind of a solution instead, so you have a displacement, and then you'll have oscillations because of this term. So if this is small enough, right? So the resistance is small enough, we'll get oscillations, but the amplitude dies down over time because of this term. So we'll see the same kind of behavior for the pendulum and for the LC circuits when we put a resistor in to make it an RLC circuit.